Alrighty. So folks, we will get started in just a moment here. I'm going to let a couple more folks join in. I'm very excited to talk about 3D printing or machining. All right. Well, I got some good amount to cover, so I'm going to get going here. And just a heads up, this is good. This is super exciting. Hey, Sarah's pinging in right here. There's a Q&A tab. So in the sessions here, you're going to see the main chat, and then to the right of that is a Q&A tab. I excel at Q&A, so I'm always happy to talk about anything that we're discussing today. With that being said, let's just run into this. So today we are going to be talking about 3D printing or machining. Know which to choose and when. And my name's Greg. I'm from Zometry, and I work in making a lot of parts with different processes. So let me just give you some background about myself, and you don't need to read all the text here. But I spent the last 14, going on 15 soon here, years in product development and manufacturing and service level manufacturing. My background has been in applied additive manufacturing, so I have been using for those 14 years additive manufactured parts in end-use states. But I've also experienced in machining, injection molding, urethane casting, sheet metal, you name it, most traditional manufacturing processes as well. And along the way, I've gained some common sense on the subject. And what I hope to do today is share some of that with you and explain, some strengths and trade-offs on each of these processes. And really, my ultimate goal here is to show you how all these manufacturing options, regardless of what category they're under, are useful tools in the tool belt and where they are useful. So some background, I work at Zometry, and we make a ton of parts. And I really mean we make a ton of parts. So from additive manufacturing, we have 8 unique additive manufacturing processes, 6 of which are polymer, 2 of which are metal-based additive. When I talk subtractive, I'm talking CNC machining, I'm talking turning, EDM, sheet metal. We do tooled processes as well. So that's scalable manufacturing, where you invest in that tool, and then you create reproductions over and over and over again. And we also put the stuff together, right? So we work with light assemblies and weldments. And really the power that Xometry has for you is it's almost like an Amazon experience. It's a click and buy experience. So you drag your parts through and get a quote, and we take care of that entire supply chain, regardless of the process or technologies that you're choosing. But what I love about this, from my perspective, is you see a lot of projects. You see one-offs, you see dozens off, you see thousands off projects, and you see where they're applied. And it's really great to talk with these clients and understand where they are in the product development cycle and where different manufacturing processes may live, including CNC and additive manufacturing. And again, just a quick summary. Like I said, we make a lot of parts. I'll just jump past this slide here, but we see just such a high diversity of geometry and applications. I mentioned this a little bit, but what makes our experience agnostic to manufacturing is our instant quoting engine. You start with that 3D CAD model, you upload it online. It actually does a couple cool things all at once. First off, it'll interpret the 3D geometry and try to guess, based off your design, what process you're likely designing for. And that's based on some machine learning. Historic orders of parts like that tend to be in FDM 3D printing, or tend to be CNC machined or injection molded. And then you can go further and customize from there. And you can always, again, if you're prototyping, switch over to another process or move over to whatever you need. But it is a highly customizable but simple to use interface, where you see pricing and lead times update automatically. And once you're ready to move forward, you press go. So let's just get to the meat and potatoes of today, though. Today is about when to choose CNC over 3D printing or vice versa? Like, where is the value of these different topics? And I'm just going to jump right into this because there's a lot to cover. And as I mentioned before, when the questions come in, let's, we'll try to tackle as many as we can at the end. And we're always happy to elaborate on anything that that you need some elaboration on as well. So I'm just going to start and just talk about what is traditional manufacturing. And usually this is interesting. I mean, it's a virtual conference. I'm a pacer, so usually when I'm doing this live, I'll be walking back and forth across the stage here. But traditional manufacturing is what we know. We're in a virtual event. You are probably looking at this through a monitor. You're probably seeing your monitor has a plastic bezel around it. That bezel is smooth. It's smooth. Maybe it has a light, soft, even texture to it because the mold that it was made on was textured. But that smooth, clean lines that you're seeing is derivative of CNC machining because that injection mold piece was machined or had a cavity that was machined. So like we have these traditional views and paradigms when it comes to manufacturing. So when I talk about traditional, I'm talking about subtractive. I'm talking about taking a bulk of something, a piece of billet or sheet, and using tooling and forming that down into the final shape. So usually that could be like end mills cutting, or it could be if it's a sheet metal piece, taking a generic blank sheet, cutting around and then bending it into shape. But when we talk about traditional, we're talking about that. It doesn't mean it's outdated. It just means, it's been there and has some legacy around. The auxiliaries are things like molding. I have to machine that mold tool. Stamping, I have to make my dies, and other tool manufacturing. But they all come back with this paradigm of my base component is taking a bulk of something and subtracting around it to create the end outcome. Specifically in CNC machining, how am I subtracting these parts? I'm using end mills, drills, other specialized tooling, and I'm cutting down those tools. So a couple things to understand with that is because I'm using these end mills, I'm removing from a solid piece of material, my end result on that surface is also solid. And that's why we can always guarantee, Zometry, that your typical surface finish is at 125 RA, and you can always select to get smoother as well. And you could actually adjust that tool approach along the way. Also note that I am spinning a tool. So some of these design for approaches, you'll understand that when I have an external sharp, I can actually take a round and cut and create that sharp external corner. But if I have an internal feature, for example, those would need to be radii because my round tool will be cutting a round corner there without any secondary process like a broach or EDM. Also understand that when I'm designing, when I'm thinking about CNC and I'm living this paradigm, I'm thinking about line of sight. This image to the right here is pretty straightforward. It's a 3-axis mill and it's very up and down line of sight there. You can see how it's approaching all those tools. If I had an S-shaped curved internal channel there, I could not mill that. And it's just one of those things where in a traditional paradigm, you're like, why would I make an S-shaped curve there? But it's just something to understand that's part of this traditional process. And when I'm looking at what drives the cost, and this is a big deciding factor sometimes, especially in low volumes, it's setups and ops in CNC machining. So when I am milling a part, I have to typically refixture it to get certain feature sets. So each one of those, we call that an operation. Usually when you're starting with a rectangle, you're using parallels or essentially flat jaws that are holding that still, and you're milling out your first features. This example image here is probably actually a tool cavity, but let's just pretend that it's going to be a more complex final part here. You will do that op one, mill at that feature set, and then flip it and do a second op. And oftentimes there's third, fourth, fifth ops, or you may run into a multi-axis machine to get different angles of approach on that tool. But as you add those operations, they have to happen, even if you're doing quantity 1, they have to happen just as much as if you're doing quantity 40 or 400 of these. The good news is setups drive price on those low quantities because they have to exist. but they get shared and amortized in pricing as quantities increase. The other thing that drives cost is how much work is that machine doing? Like, what are the minutes or hours that's doing cutting and defining these shapes per operation? And we call that overhead. Machine overhead can be high, especially if it is more expensive style machines. So 3-axis are pretty literally, no pun intended, run of the mill. But 4th, 5th axis, 6-axis live tooling lathes may have a higher overhead rate against them to do certain complex geometries. And also, when I am cutting a machine part, often it's a machine, and approach. So there's finishing, there may be quality assurance requirements, CMM inspection, etc., and those can all drive cost in. But this is what you get out of it. We know what it is. When I CNC machine a part, I know what that alloy is. I don't really question 6061 T6 when I order it. It is highly characterized. It's available through multiple distributors. The chemical composition of it has like ASTM standard behind it, and it's just something that is almost textbook because of how regular it is in our manufacturing ecosystem. I could also, when I'm cutting these parts, I can hit very precise tolerances and feature sets. And that's because I can slow down or get specific tool sets to create features on those machines. Think about a CNC machine as essentially a generic tool that can make lots of different things inside it. So CNC machines that are generalists, the experts are really the people that are operating and running that cam and sitting there setting up those machines and those programs. CNC is also, it's just been around. So it has an established track record. It has production use cases. And again, it's something that intuitively you don't really question. But it's really interesting when you look at new technologies, we'll segue to additive in a moment, about, wow, look at all this trust I have in CNC, but additive, look at all the stuff I need to do to gain the trust in it. And I just want to note it's not your grandfather's machine shop here. Turnaround times for CNC are not as challenging as they've been in the past. For simpler parts, you can get 2 to 3 business day lead times. You can get short lead times on machine parts. That being said, as you add complexity to the part, as you add quantities, it does stack up. So although we can start in just a few business days or ship within the week of your order, depending on the complexity of the part, that also can require more time, up to weeks on those parts there. So I got an example of this. We actually manufacture parts for a micropropulsion unit for Phase 4 aerospace. And we've done a case study with Phase 4 about this, which is great because we make so many parts and I can't talk about any of them. So I love it when customers are like, yeah, you can talk about this one. But this is something that absolutely needs to hit critical needs. And let me just explain that, because even aerospace parts can land and you can maintain them. But space flight parts, especially satellite systems, there's no maintenance and repair opportunity. So you need to know the metal that this is made out of just has to hit your physics and your simulations exactly what it is. You need to have your NADCAP level finishes exactly to their specifications. You need to have the quality standards and material traceability and other requirements at such a high documented level that CNC machining just makes sense for it. And I wanted to show this example because this is a for microsatellite systems. This is stuff that is designed to be in space, and for this particular application, it needs to be CNC machined. So, and then by the way, again, reminder: if you have any questions, please go along. We're always happy to talk more, and even some of these case studies, which are pretty cool, I could tell you what I know, on those. So let's talk about this now. What is 3D printing, right? And 3D printing is a little bit different. I am not taking a large bulk of something and removing material down from it. I am joining materials together or fusing them together in a way, and based on a 3D model, typically building from the bottom to the top to form a final object. I'm going to use additive manufacturing and 3D printing synonymously. I didn't always use that, but the industry's kind of absorbed those two terms together. So, hey, I'll live with it. But it is a way of growing parts. And I use the phrase growing very often when I talk about additive. It's taking something less and then creating something more out of it. Some synonyms again, additive manufacturing is most popular. You may see some of these around, but they're not as popular anymore. But there used to be a little bit of a war going on what to call this stuff. And as I mentioned, Zometry, we do a lot of these processes. So if I'm taking a powder, for example, a powdered material, like a powdered plastic or powdered metal, I have a few of these powder bed fusion processes to make parts. And typically you're going to run with HP multi-jet fusion here, selective laser sintering. I got a couple examples right behind me of some SLS parts, or direct metal laser sintering. So these all have strengths and trade-offs, but understand their base is powder material and they're being fused by a laser. I can also cure a resin. So if you've ever had a tooth filling and you've seen them put that UV light in the back of your mouth there, that is actually a photopolymer. And there's photopolymers in that same aspect. You can take a UV projection or take a UV laser and cure a photopolymer for it to selectively harden in a state. And that's how we have the invention of stereolithography. Actually, the 1984, the OG of additive manufacturing processes. PolyJet 3D kind of turns it on its head. It's more like a inkjet printer, but the droplets have some thickness to it and they get cured along the way. So you build from bottom to top. And then carbon digital light synthesis, and I'll touch base on this a little bit more, has a little bit of an evolution in the material science behind that to help create more end-use applied parts for it. But they're all starting with a base material of a liquid and creating a part. And then you have processes, if you're used to desktop machines, you may have seen a filament-based machine that extrudes a filament, melts it down, zigzags back and forth and builds. That would be called fused deposition modeling. We run the hulks of that. We have more industrial machines, but that is a baseline where I can actually interchange materials pretty quickly on that and build boutique manufacturing. So why do I call it industrial versus desktop? Because of reliability and repeatability. As a service provider, we are looking for something that I can hold a data sheet up to and say, this is what you're going to get. And I could also consistently make a part. So you can order one today and then order 33 months from now and get a consistent experience. This is a little bit of actually Zometry's internal additive lab, and we have a massive network of manufacturing partners as well. And this is just some FDM lines here, but these are some Fortis 900s on this side, Fortis 450s on this side, and we have 21 of those FDM machines in our building. But yeah, we use these to grow parts all the time. We run 3 shifts, 7 days a week within this platform. So there's a lot of value added with additive manufacturing. Understand though, I'm not cutting that material. I am growing it. So when I grow that part, I do have a layer by layer by layer residual outcome where I can actually see more surface roughness. For example, a powder-based process may be grainy. A filament-based process may have some stair stepping. Resin will be smoother, but there are also some trade-offs that I'll discuss a little bit later. But understand that surface finish is not the strength of additive, because you're not taking a solid material and then just slicing it down. It starts with something less, and as it grows, some of the residual nuances that happen on how I'm fusing and bonding that material together will actually show on the outer surface of that part. That being said, I can make what I want with additive. I can grow, I could create very complex organic structures because additive is very forgiving from traditional mindsets when it comes to design and paradigms. So complexity, we call it complexity is cheap. I won't say free, but it's cheap in 3D printing, and it often favors a more complex design versus a bulkier, hockey puck design when you're 3D printing parts. So what drives my cost in 3D printing? It's going to be the material volume used. So how much stuff am I depositing to make this? It's going to be a machine overhead, because unlike a desktop machine that may be hundreds of dollars, these machines are still tens of or hundreds of thousands of dollars. So they have a higher overhead rate to them. and secondary finishing. So as I mentioned with CNC machining, that could be a post-thermal treat or a chem film or some sort of part marking. Secondary finishing with additive is typically more around getting the surface treatment to act or behave a certain way. For example, surface smoothing, water sealing, some sort of cosmetic finish to it. But those are the things that are going to be driving cost. So what's some cool stuff that additive does? Additive manufacturing, it is the king of prototyping, or queen. It's super powerful for prototyping because you have low or no setups required. You're essentially just reserving the space in that particular machine and platform to build your specific geometry. It is, just very, very useful, especially in the product development phase. Even if you're looking to eventually use another process, you may be using additive in parallel to just validate certain aspects of your design. The turnaround typically is short. It's typically 1 to 3 business days. And some of these processes can scale better than others. So some processes like FDM may be more serialized in the production route, but other bulk-based processes like multi-jet fusion or even carbon DLS can actually produce dozens or hundreds even per evening with these machines. And those could be even mixed, so hundreds of unique items or hundreds of single of one item. They're kind of a very forgiving technology for that. The other beautiful thing is because that complexity is free, designs can be function oriented through the adoption of this freeform geometry. So I always call this purpose design. Like I'm building features where they are needed and building a geometry to either connect that, but I have some more freedom if I need to create lightweighted structures, or if I want to do, I've built parts before for electronics manufacturing where it's like, okay, this is a rigid structure, but let me just put a little lip here for cable routing. Like you do some clever little things with an additive design, and it could help reduce your part count significantly. And what's awesome about additive, especially from what I've observed in my career, is that it has significantly reduced the barrier to entry for getting into a manufacturing technology. All you need is a 3D CAD model. And 3D CAD, the barrier to entry for 3D CAD has also reduced. So I know we have Fusion 360 app for Zometry now available, but you can get very professional CAD for pretty cheap. So those two combined make it very easy to enter into the 3D space. And 3D used to be this unique thing that was niche. And now sometimes 3D is the first manufacturing experience that designers have. So let's talk about what I can do with the ability to niche designs and one-offs. I think a really good example you see a lot is tooling of fixtures. So I have a case study here of somebody who needed just that, Dixon valve. This is actually a fixture for a secondary process of an investment cast object that they have. And they needed a design that was all in one. It had to be tough. It had to be metal. It had to be aluminum. But the way it was designed had to mate with their casting unit in such a way that to traditionally machine it would be a multi-axis, fifth axis design here. And surface finish wasn't as important as just the strength and function of it. So you're actually getting a twofer in this picture here, because the hero is this direct metal laser sintered piece, so a metal 3D printed component that if you look at our case study, you could actually see some more of the geometry and how complex it is. But what's even more clever is the base that they're holding this fixturing piece to hold their investment cast in is also a 3D printed design. So very purpose-built, very significant. Like, I need to hold this. Let me build the feature set to hold this here. I need to hold this. Let me build this feature sets exclusively for this feature. And you can kind of cheat and not think about traditional manufacturing rules. But it does require a paradigm shift. So again, I spend a lot of time on additive because additive is usually the paradigm shift from the machining standpoint. I do a couple things differently with additive. I'm not thinking about how to approach my design by cutting away material. I'm thinking bottom up. How is my design actually going to grow? I stole this slide from our How to Design 3D Printing or How to Design for 3D Printing webinar that's linked in actually Zometry's booth if you want to check that out. But you have to think bottom up, and you have to think about how your feature sets are designed to be optimally oriented, especially if you're designing for production of an additive component. You could get away with creating a design for rapid prototype just by putting the CAD and going with it, but you can really optimize for this process as well. It's also really important to think about what the outcome is. All additive manufacturing creates a near net shape. As of now, I hope like they're like, 5 years from now they're like, no, it doesn't. But right now, all additive manufacturing creates near net shapes, which means that I'm calibrating my machines usually using something like a calibration cross, and that will be something that I'll print out, measure, put in those inputs, and the machine will automatically update some scale and offset parameters to help tune the machine and create more consistent parts. That being said, you are not making calibration crosses. You are making whatever your part is designed to be, and it's doing its best based on that information to make those shapes. But unlike CNC machining, I cannot slow down to an edge and say this edge right here is going to be +0, -2. I need to look at the part from a more holistic perspective on what the outcome is going to be. This can mean a couple things. One is you can look at some of the Zometry's design guides for a specific process and put some face offsets on critical features to help compensate for what probably is going to happen when it builds. Or you could build your part and measure and adjust the CAD to that. Excuse me. So the other thing to know is that, and by the way, when you're adjusting that CAD, we call it tuning, like tuning the part. So if I'm building something for production, I may expect a few rapid iterations before I build multiples of that, and that's just to make sure that all my mates and all my fits work very well before I move into a production additive component. So the next thing is that many additive processes do require support structure. That support structure is there to actually create a platform away from the platform to hold part features as they are forming. A good example is if I have the letter T, I could grow the column of the T on top of itself because there's something for it to grow on top of. It's basically like a tree trunk. But as soon as it goes out, there's nowhere to deposit material. There would just be empty air. And so my material would just kind of flutter away. I create a sacrificial support structure that grows along with that part that then the actual part features can grow on top of, and then we remove afterwards. Sometimes that's soluble. Sometimes it's the actual part material. For example, direct metal laser sintering is a part material. This image here is a part that we actually made with carbon DLS epoxy, so EPX. And to show you, you see those lines right there. Those are actually little stipples from where the support structure was removed. So something to understand is if you have critical surface or feature tolerances, sometimes going back to part one here, thinking bottom up, and that orientation becomes really important if you're trying to mitigate support in those specific areas. Where we don't have support, we usually call it growing natural, by the way, some industry terms, so like a natural growing feature. The last thing when I'm talking about paradigm shifts for additive is to think about resolution. Because this is an umbrella topic of different manufacturing processes, I like to use analogies a lot from Sharpie pens and pencils to get an idea of like what you're going to receive. When I am beaming a laser down, so laser-centered parts, multi-jet fusion parts, DMLS, I'm exposing those to heat in some way, there's a little bit of a thermal bleed that goes on. And that means that it's pretty dang good at feature resolution, but small features may have a little bit of a over-center, especially in confined areas like holes. And that's why I use, for a good example, a Sharpie permanent marker, like a fine tip there, where it's very good detail, but there may be a little bit of a bleed. DLP and laser-based photopolymers, so UV laser-based photopolymers, they have a much better surface outcome to them. There's it's not perfect resolution, but it's much more higher detail. And I'll move that to my Sharpie pen as my analogy. And in FDM, because I am building stuff with an extruded layer of plastic, extruded almost a line, I put a 1.1 millimeter markup pencil here as an example, but think of it as a markup pencil with like a Tron bike where it can't overlap itself per layer. And That means that if you're trying to color in or trace small features with a very thick pencil, you can understand how that may sweat the small stuff. And I'm going to go very briefly over this here, but just to kind of show you like there's options. So when we're thinking about machining, when we're thinking about additive, machining is a general purpose thing that you put your material and you make your shape. With additive, it's a family of platforms out there. Now these families of platforms, you may choose one over another for different applications. I have a webinar that's focused a lot more on this particular topic here, but my biggest point of this is there's a lot of options available in industrial additive, and it all starts with what's my goal? What am I trying to achieve here? And that could be making a part that maybe is for a prototype that needs to be clear. It's very quick to jump down to a couple clear options of 3D printing. But if I want to go functional, a lot of times it comes down to my end use application, and it's going to bring me into a different process tree, and then specifically some materials within those processes. The other thing to note in additive is that there are limitations. So this part here is a rigid polyurethane part made in carbon DLS. And a part like this, I could grow maybe 3 or 4 on a platform at a time. But the platform is pretty small. So say you actually have a part that's 4x the size, and you're like, I love this material. I actually may be platform restricted and may need to find an amicable substitute in a different process. So again, unlike machining, additive still is very much on what's confined to the platform. Our largest being a 36-inch platform for FDM, and SLS and MJF and SLA kind of being the generalist round, but there's also some processes that are much smaller. I often get that question asked when we talk about metal 3D printing, because you're usually confined to sub 9 inches. So running through a little bit of these processes and materials, and again, if there's any questions along the way, always happy to talk a little bit more about this. But what's the strengths, what's the trade-offs of these? So when I look at SLS and HP multi-step fusion, I have a strength in that I'm building real polymers, and I could build in bulk because I do not need support structures. In fact, these process sets are the vast majority of 3D printed polymers out there from an industrial side, not a non-desktop side, because you could just crank out parts, and it is so forgiving on geometries. Materials like nylons are extremely forgiving for even fine details because they flex before they break. So even when a part is not best designed for the process, a lot of times the features survive on it. But you also are often stuck with a choice of nylon, filled nylon, another type of nylon. Polypropylene just launched, so that's really good, and some TPU, but you're really stuck with nylon or nylon with this. So it becomes very limited in the choice. If you could use it, it's very great, but you're also limited with the material. You can see here, this is a 4-inch part here, and you kind of see that kind of grainy matte surface finish to it. Now, that being said, if I took a bandsaw through, the part would be completely solid on the inside. So that's just a superficial graininess to it. Notice that surface grain also shows up when I do direct metal prints. So direct metal laser sintering creates parts in steels, aluminum alloy. We have nickel alloys. We have titaniums available as well. And the power here is I'm making a metal part that I could do cool stuff like this with, right? I can eliminate upfront tooling if I'm looking for something like a cast surrogate. I could build complexity into it, but I understand that I should have expectation that the surface roughness of this part inherently will be similar to a investment cast where it has that inherent roughness, and that's because it's based on a powder and a laser's fusing, and you have that external characteristic from the base material and how it kind of splashes when it welds. When I use this, and I'm competing versus machining, I really have to look at where the value add is. Sometimes it's lead time versus complexity, like that Dixon valve. But if I'm just making a part that could be machined, it actually be maybe a more expensive option than just straight up machining the part itself. So you're usually approaching metal additive manufacturing more as a premium design for manufacturing experience. So it's much more of a consultative or engineered approach, typically, especially if you're just slightly beyond the prototyping side. I mentioned this FDM is very boutique. I can put a bunch of different plastics into that filament canister, and I can extrude them out and make these shapes. And I can print big. I can print up to 36 inches. So ABS, ASA, nylon 12, polycarbonates, Ultims are all readily available everyday materials in this type of platform. It does have a much higher variety of plastics, especially if you include desktops and FFF out there. Than any other 3D printing process available, as well as if you expanded that, it's just very, very highly accessible because these machines are typically easier to operate, and again, you're able to interchange materials regularly. But I am, drawing with a crayon. It will sweat small stuff, and you do see that visible layer stepping as you move layer by layer. So a nice increasing contour like this, kind of turns out to be pretty beautiful on how the design comes, but the more shallow you get on those contours, the more noticeable that stair stepping will be. The other note is that per machine, you're typically extruding, a filament at a time, and that means that if I build 12 of those, it's just 12x the time. There's very little time saved by arraying prints, other than some stuff that happens on the layer by layer basis, so like tool head cleaning and things like that. But it is a slower throughput machine than a lot of other processes out there. And SLAs, photopolymer resins, so what are photopolymers? They act like materials, but they're actually thermoset that are usually epoxy based. So when I say ABS-like or polypropylene like, they have some characteristics like a hardness level or a little bit of a flex before break, similar to those, but other feature sets are not identical. And it's important to note that polymers, I've broken a lot of parts in my lifetime. Polymers, like real plastics, they just survive so much faster than photopolymers. I actually did a test called Will It Tumble, where I took a SLA part, or I actually had 14 different additive materials of all different processes. And SLA, like this is accurate clear view, in 16 seconds against the test. And it was almost completely destroyed. Meanwhile, I have a HP multi-jet fusion part with a vapor polish finish that hung out for 10 minutes of the test and had just a little bit of minor damage, just to kind of show you like how different some of these behavior properties are. But SLA is beautiful. I just said that clear part, absolutely wonderful. It's great for concept modeling, prototype. It just doesn't translate into the production world. Bridging that SLA gap is carbon DLS. I showed you that RPU, the rigid polyurethane part that I have in my hand. But this picture of this is actually an epoxy part here, but it bridges the gap because of material science. So it is curing parts in the same way that a liquid photopolymer would cure. It's using a digital light projection approach, but the secondary step is a post-thermal cure. So you end up getting these really nice, dense, isotropic parts that have an SLA style surface finish, but have more of a longevity of a plastic part. So it's it's very exciting because that helps kind of bridge that complexity and use paradigm that you may run into, especially when you're thinking about long use qualified materials versus CNC machining. So some things on the horizon though that's very exciting is, how can I make my additive parts look more like a machine component or more like a molded component in some ways too? And we have some manual processes that we do. We have some newer processes as well that help really significantly increase accessibility to things like surface polishing or surface smoothing. But first off, yes, you can machine these materials. But as soon as you start machining these materials, and again, choosing between additive and CNC, unless you have significant value added within that additive component, the second that you're machining it, you should be asking yourself, why am I not machining the entire thing? So if the part has, a lattice interior, grow it, then machine it. That's fine. But if the part is just solid and you're trying to get an O-ring groove, it may be more beneficial to stick with a traditional process. Media tumbling is touch-free. It helps bring some of those surface finishes from a coarse grain down to like an eggshell, but it's not a glossing option. Chemical vapor smoothing, like this image down to lower right. So this would be a natural, and this would be the vapor smooth with a dye black at the end there. That is actually a more scalable process to take additive components, particularly for FDM, SLS, and HP multi-jet fusion, and give them more of an end-use cosmetic. Also, when you polish the surface of a part, you inherently increase the performance properties of it. It usually has a better flex before break, better tensile modulus, because it's evening out the stress, so it shares the stress among the surface layer versus having unique peaks and valleys that will have little micro stress points that could cause a fracture on the part. You can do mechanical polishing, so that's sanding, very fancy word for sanding, that you could bring parts down. But the second that I touch that, I add labor. And now you're paying for a person's overhead rate against that part. And I wanted to show this. So electropolishing, a lot of people think electropolishing is a miracle cure when it comes to additive metals. Typically, I want to bring my part to a smooth state and then electropolish. There's some better processes out there. Like this is actually a picture from D-Light's dry electropolishing process that can bring a much better gloss with longer duration without heavy feature loss. But electropolishing typically only removes about a tenth, or like it is a tenth of a 1,000th of an inch of material. So if you have a rough part, you'll have a brighter rough part. But if you have a smooth part, it will really enhance that glossiness to it. And a lot of our parts, you can add coatings, epoxy, sealants, dyes to enhance the properties. But again, you are going to that range of, am I adding a manual overhead rate against these parts? So what does this all mean? I just spent a lot of time on 3D because it's not just one thing. It's CNC machining is easy, right? I have a part, I cut a part, I have tool sets, but it's a one machine that could do so much. 3D printing is a range of machines that are out there that can do a lot of good things, some better than others, and there's strengths and trade-offs to each. When I think about 3D printing versus CNC machining, and as a designer, some of these value props come to mind. So if I have a large, bulky geometry, we noted volume is a cost driver when it comes to additive manufacturing because it has to do more work to grow that part. With CNC machining, a big bulk of metal is actually less work. It's like, oh great, I don't need to mill out those features. I'm cheaper. So CNC machining, that's actually good. It's a lower cost driver than 3D printing, which is a higher cost driver. And the opposite though, when I'm adding this coring and lightweighting features, 3D printing just loves that. It is very used to doing those complex geometries and building those out. Where CNC machining, you're adding work. You may even be adding specific tool sets, or you may even be making features that are just impossible to traditionally machine without complex equipment or just at all. Similar with off-angle holes, which kind of flows into this complexities of free argument as well as organic features here. I can go off angles when I grow parts additively. I can make parts in different directions and make them more purposefully designed for that intended application. Machining has those rules of angle approach. So if I have off-angle holes, I need to use a higher overhead machine or increase my setups to get the angle right to approach those features. Additive, I can just grow that out almost like branches on a tree. The same goes for those organic features there. So that stuff drives machining costs up, but is a value add for 3D printing. So if I'm looking for 3D printing as an end use, this is part of my tool belt now. These abilities, and actually it's favored a lot of times in these processes. The other things that I'm looking at though is like precision. I need these features. I need this array of 18 holes to hit a true positional tolerance of 0.002, and I have these datum conditions that are required. I need need to hit the entire geometry off feature sets to hit plus or minus 5,000s here. That is very difficult when you're dealing with a near net shape without some sort of post processing or developmental tuning. So iterative design where you're measuring and testing your outcomes. So that's cost for 3D printing. In machining, just give me your drawing, and we'll cut to print. It's much more straightforward with that. Smooth surface finishes. We just talked about, going back, I can do some smoothing, but it's nowhere near even the natural finishes that you could typically get with machining. So if that surface finish is a high requirement, a lot of times that is a stop when it comes to additive manufacturing without significant post work to that. And the last thing I have here is deep holes and channels. I can do some very unique geometries with additive because I just need to worry about what's underneath it. Can I grow, and stack those layers up to create and form my feature? Typically, deep holes and channels would be a wire EDM or RAM EDM or some sort of deep hole drilling where you need specialized tooling or just expect some tools to break. This is a really powerful thing that you do with 3D. You can make tubular channels and other features that go throughout the part, and cooling channels is a really good example of that. That would something you just couldn't traditionally mill. But this is when I think about design and I think about how, as a designer, I'm building out my parts. Like, these are really some considerations that I have on strengths and trade-offs, and understanding like where, based on my design approach and my intended outcome, this may be make or break for different technologies. So just to recap and talk about this, machining versus 3D printing, and I kind of separated this out in metal and polymers just to help out a little bit. But metal 3D printing, you're not going to take something that's a great CNC part and just metal 3D print it, or you can, but you may just have better value machining it unless there's a purpose-built design, unless you're using those organic features or off-angle holes or all-in-one assemblies, those value props that you can add when you metal 3D print. It is good for low volume, but that build size is limited. So when you go into production, smaller parts can be produced. So parts about like the size of 2 fingers together in high production, or you need a lot of machines to produce in parallel for that. Cast surrogates are a great intro. So if you're investment casting something or die casting, usually you could take those models and directly look at it in metal 3D printing. In fact, actually a lot of die casting, I think A360 is ALSI10MG, so it's a silicon magnesium aluminum alloy, and it's equivalent in additive metal. So the one thing well, actually, yeah, that's that. It's actually a very nice drag and drop approach, and we see companies that have requirements of less than 24 a year move to additive manufacturing versus investment casting, just because of weeks and weeks and weeks of lead time versus getting your parts in 6 days. It's just so much more valuable for them, and they could just put it on their own machines and do some post work that they already have set up for their traditional process. And I mentioned those all-in-one assemblies. When I think about polymers, obviously like the one-offs, fixtures, fit checks, that rapid prototyping, as I mentioned, I don't need to pay for tooling. I don't have upfront costs, so it's very easy to go through and validate something. When I talk about a design approach and product development, even if you have a larger assembly, sometimes you use additive to validate a specific part of that, validate a fit check or a seal on one specific part, and just essentially cut it out of your design and make it. And it's very, very cool to do. You can scale smaller pieces to production, but the larger the piece is, the more limitations you have on platform size, and with the more process like machining or molding is going to become more useful to you. And also, additive doesn't care if you've changed your rev. Just put your new rev in. We'll print it into the next run. And so it's less sensitive to revision changes versus a process where you may have setups already involved. And a revision change means brand new setups. And so you're essentially starting at square one on a cost basis. So when I stick with CNC machining, large chunky parts, as I mentioned before, CNC machines, they're generalists, they can do that. The more materials left behind, typically the less expensive that it is to machine. You have the material cost and the machining time on it. Critical surfaces, just if it's an absolute must, it's so difficult to hit that with additive and qualify and have that repeatedly done. You can, but with machining, it's just part of its nature. Same with tight tolerances and stringent specifications. We know, like, we have such a good standardization of those materials and metals. That's why Phase 4 Aerospace, for their satellite program, needs a machined part. They need this material traceability. We could go all the way back to where the ore was mined on that and move it all the way forward to where and how it was milled. I mean, it's just a complete track record with it. And the material itself, is industry qualified. but these are not mutually exclusive. Just understand that 3D printing typically is part of your product development cycle, and it bridges, bridges a lot of these goals with, longer lead items and shorter lead items. So, oh, and actually, I forgot I had this in here. Here's a good example of people who get it. I actually, BMW, and BMW actually became an investor of Zometry after they became a customer of Zometry as well. Ryan Lambert, a tooling engineer down in the North Carolina plant, they and his team, they do an incredible amount of custom jigs and fixtures for the vehicle assembly. I think it's for the Model X line, and they actually know where the strengths and trade-offs are. So every time we make these fixtures for their team, which is every week, by the way, we're constantly building these parts that are always unique. So these would example, like this one here would hold a BMW decal that would be on like the back right of the vehicle, for example, and it would allow you to gently press it onto the tool. And these features down here would be to help it align to the vehicle body consistently every time they put that on. What they found was anything that had a long extension to it, it needed full rigidity. They usually would CNC machine out of aluminum or Delrin because they just needed it to be like, it needed to be exactly to specification. But they found that features that needed to hug something, create custom contours, or just envelope certain features or combine them together. So essentially the main body, the unifier of these designs was perfect for 3D printing. And they love the fact that with 3D printing, you could also often do color to that. And even for FDM, you could do infill changes. So these are work holding tools. So if they can make the main body, the thing that kind of hugs the overall vehicle, mostly 3D printed and lightweight, they could reduce user fatigue and actually increase the quality rate of the production line. That being said, though, if they need specific spots to just be like exactly to tolerance, they're adding machine parts to that. So, it's really cool example to see just this high variety of different use cases that are mixed in with just one assembly. So both additive and subtractive manufacturing. And I just want to note again, like, for us, you could order your additive parts, your subtractive parts. You could put urethane cast all in one order. And just press go. We take care of the rest. I'll segue. We actually have a code for you all called CAD Beast that you can use at checkout. So I'll have a note of that at the very end too. But the instant quoting site's really powerful. It takes most native CAD files. You could upload that, or a step is always, it's like the PDF 3D CADs, and you could actually go and get a quote and check out how these different processes compare in pricing, and even change some quantities around. It's really unique. Like if look at a quantity, 1 in 10 of something, and change it to SLS versus MJF, you may actually get some very surprising results. If you like just living in your CAD, like a lot of us do, we actually have add-ins that work directly with Inventor, Fusion 360, and SolidWorks. So if you go under our Zometry's website, the Resources CAD add-in page, you can go and download those free add-ins and install them right to your systems. And we have obligatory, we have a great referral program. So if you are a Zometry customer, you can go to the upper right, earn credits, and get a referral link that you can send to others. If you send it to them and they register, they get $50 that they can use against their first order. And if they order, you get $50 too. So that's a great little earn credits thing. And if you're logged in, you'll see it in the upper right-hand corner of your browser. The other thing to note is that we talk a lot of subjects. We talk about machine tolerances. We talk about making good drawings. We talk about designing for 3D printing, specific 3D printing technologies at Zometry, because we experience so much of the manufacturing world there, and we want to share that with you and to have these resources. I really recommend, and I actually have some of these linked in Zometry's booth, so you haven't been there yet, go there, download some of that. But definitely check out some of our videos that we have on Zometry's YouTube channel, some webinars that we have, and I do a fun edutaining series where I just break a bunch of additive parts to show how they compare against each other. We have great downloadable design guides, and we have our case studies, some of which I highlighted today. We have fantastic customers from all sorts, sort of independent inventors all the way up to, stuff in space. And we're happy to make parts for every industry out there. And I see, Sarah mentioned, this is time for Q&A. If you guys want to chat, I'll be around, and we could always also touch base at Zometry's booth in the chat afterwards. But otherwise, yeah, thank you so much. Please feel free to go to Zometry. We do have something just for you all today. CAD Beast is a $50 promotion that you can use. It's a single time use, but you can use it on your next order if you want to try out a different process, or if you're trying to figure out, hey, will 3D printing work for this, or CNC machining? It can help you move along the way as well. All right, I'll hang out for a little bit. Actually, I don't see any questions. I saw one was answered, but it was answered while we were talking, so. All right. Well, if we don't have any questions, I'm going to buy you guys for 4 minutes, and I will see you back at the booth. But again, really appreciate your time today, and thank you so much for attending today's webinar. Thank you.